Hello students, in this video lecture we shall see how to calculate inductance of a transmission line, whether it may be a single phase or it may be a three phase, by taking some examples. Okay, in the last video lecture we have solved the problems on single phase transmission line. Here we will be calculating inductance of a three-phase transmission line. Let us take the example. Calculate the inductance of each conductor in a three-phase, three-wire system when the conductors are arranged in a horizontal plane with spacing such that D31 is equal to 4 meter, whereas D12 is equal to D23 is equal to 2 meter. The conductors are transposed and have a diameter of 2.5 centimeter. So this figure shows the arrangement of the graphical representation of this problem. See, you can see that 1, 2, 3 are the conductors, and D12, D23 and D31 are the distances between conductor 1 and 2, D12, conductor 2 and 3 is D23, whereas D31 is the distance between conductor 3 and 1. He has given that the distance between 1 and 2 is 2 meter, distance between 2 and 3 is 2 meter, and the distance between 3 and 1 is 4 meter, and the diameter of each conductor is 2.5 centimeter. And what is to be calculated is the inductance of each conductor. So we know what is the formula for the inductance. Inductance per phase per meter is given by 10 raised to minus 7 into bracket 1 by 2 plus 2 natural log of D equivalent by R henries. Okay, and what is this D equivalent? This is the equilateral spacing. Okay, all these are, they are spaced equally. Therefore, D equivalent is given by cube root of D12 into D23 into D31. Okay, substituting the values of each which has been already given, we'll get is, what we'll get is 2.52 meters, which is nothing but 252 centimeters, because D equivalent and R should have the same unit, whereas the radius of the conductor is diameter of the conductor divided by 2. Diameter of the conductor is 2.5 centimeter. So what we will get is 1.25 centimeter. So substituting the value, what we will get is D equivalent is 252 centimeter and R is 1.25 centimeter. So what we will get is 11.1 into 10 raised to minus 7 henries. But what has been asked, this is the 11.1 into 10 raised to minus 7 Henry per meter. Okay, what has been asked is you have to calculate the inductance per kilometer. So you multiply this, that is 11.1 into 10 raised to minus 7 into 1000. So after calculation, what we will get is 1.11 millihenry. This is the inductance of each conductor. Okay, so what is important you should note here is you have to calculate what is the equivalent distance, equilateral spacing you need to calculate. Okay, so once you calculate that, substitute this in this equation, we'll get the inductance. Fine. This is one example. Let us take another variety of example. Okay, this is another variety of three-phase transmission line. Okay, Figure shows the spacing of a double circuit three-phase overhead line. The phase sequence is ABC and the line is completely transposed. The conductor radius is 1.3 centimeter. Find the inductance per phase per kilometer. Okay, this is the problem. This is the figure that is given. So the phase sequence is, this is the double circuit three-phase line. So there are 6 conductors. The sequence is A, B, C. Okay, and this will be A dash, B dash, C dash. Fine. Now we need to calculate what is the inductance per phase per kilometer, right? Okay. So what is the formula for inductance per phase per kilometer? Let us say per phase per meter, standard equation. Okay. So inductance is given by 10 raised to minus 7, 2 into bracket 2 into natural log of dm, natural log of dm by ds. Here dm is a mutual GMD, geometrical mean distance, whereas ds is a self GMD. Okay, so self GMD is given by, see, you need to calculate what is self GMD. If you recall, that is the r dash. So the distance between conductor A, okay, A, okay, right, or A dash, right, A, distance between A dash, and what is the into bracket distance between A dash A into A dash A dash. Therefore there are 4 parameters. Therefore it should be under 4th root of AA, DAA, DA dash, DA dash A, and DA dash A dash. Okay, this is in position 1. So there are how many positions? There are 3 positions, right? So you have to take the equivalent of this, all these 3 positions. So the equivalent self GMD of one phase is given by ds is equal to cube root of ds1 into ds2 into ds3. Okay, why 3? Why we have to take 3 self GMDs? Because it's a 3-phase line and it is completely transposed. Okay, so where ds1, ds2 and ds3 represent the self GMD in positions 1, 2 and 3 respectively. Okay, and also ds is the same for all the 3 phases. Fine. Now let us calculate what is ds1. Just now I have explained. ds1 has 4 components: daa, daa dash, da dash a, and da dash a dash, right? The same thing I have written here. And what is this daa and da dash a dash? This is nothing but a GMR of a conductor, that is r dash. R dash is equal to 0.7788 into r. What is our resistance? Radius of conductor. Radius of the conductor is 1.3 centimeter. So what we will get is 1.01 centimeter. Okay, daa. Now, what is the distance between daa dash? A dash. Okay, if you draw a line, it will be a hypotenuse. Okay, so hypotenuse of a triangle like this. This is so that is a dash is given by under root 6 square plus 6 square. How much you will get? 8.48 meters. Okay. So ds1, you substitute the values. ds1 here, daa is 1.01 centimeter. Okay, convert this into meters. This is in meter. So 1.01 into 10 raised to minus 2. daa dash is 8.48 meter, and da dash is 8.48 again, and da dash a dash is 1.01 into 10 raised to minus 2. The same thing I have written here, 1.01 into 10 raised to minus 2 into 8.48 into 8.48 into 1.01 into 10 raised to minus 2. So after solving this, what we will get is 0.292 meters. Okay, and this will be same as that of DS3. So this is same as that of DS3. What is this DS3? DS1 you have calculated, that is D of AA, D of AA dash, D of A dash A, D of A dash A dash. Similarly, D of DS3, that is in third position, that is D of CC, D of C, C dash, D of C dash C, D of C dash C dash. This is same as that of DS1. Okay, so that will be same as that 0.292 meters. Now DS2 we have to calculate now. DS2 is dBB, dBB dash, dB dash B, dB dash B dash. Okay, that we will get it as 0.246 meters. So now you have to calculate the equivalent equilateral spacing ds, and that is cube root of ds1 into ds2 into ds3. Substitute that, we will get 0.275 meters. Okay, now we have to calculate the equivalent mutual GMD, that is dm is equal to cube root of dab, dbc and dca. Okay, this DAB, DBC, DCA is a mutual GMD between AB, BC and CA. Okay, then what is DAB? Mutual GMD of AB is, it is the distance between AB, okay, then AB dash, then A dash B, then A dash B dash. This is DAB, DAB, DAB dash, DA dash B and DA dash B dash. This is mutual between A and B. Okay. And what is DAB? You know, what is the DAB? Distance between B and D? 3. Okay. Distance between A and B dash is under root 3 square plus 6 square, right? This is the distance between A and B dash, that is 6.7 meters, and A dash B is same again. A dash B dash is also 3. Okay, finally what we will get is 34.48 meters. This is same as that of your BC, that is BC is DBC, DBC dash, DBC, DBC dash, D C dash B and D C dash B dash. Okay, see DBC is 3 meter, DBC dash is again under root 6 square plus 3 square, that is 6.67, and again D B dash C dash, that is again 3 meters. That's what has been calculated here. That's same as that of your DAB. Now you calculate DCA. So what is DCA? The distance mutual GMD between C and A. C and A, right? DCA, DCA dash, D A dash C, then D C dash A. Okay, it's a mutual GMD between C and A. DCA, DCA dash, D C dash A, D C dash A dash. Okay, so what we will get is, okay, what we will get is 6 meters. So you see, if you substitute these DAB, DCA, DBC in mutual GMD, what we will get is 4.94. So we know what is DM, what is DS. You substitute these equations in the inductance per phase per meter. Finally, what we will get is 0.57 millihenry. Okay, thank you.